All right, welcome back. Any questions before we begin? I'm hoping that the energy unit you guys have done a lot of already, so it's not, hopefully there's not too many questions. It's not working. There we go. Okay. So, come on. So work is force times distance. Now, there are a few questions where there's angled forces, and that's what we're going to talk about right now. It's, if you think about, like, let's push an object on the ground that way. Okay, this force is doing the work because it's like the distance that the block is going to go is that way. Okay, so the FA that's doing the work and the displacement of the object are in the exact same direction. If you have if you have an angled force, so you're pulling it like that, then part of the force, so if you break this into components, part of the force, the FA that's in the X direction, is doing the work, and then part of the force, FAY, isn't doing anything. Okay, it's not changing energy at all. Okay, the FAY isn't lifting the object off the ground, so it's not giving it potential energy, and it's not contributing to the change in kinetic energy. Only the FAX is. And so instead of saying work is force times distance, we would say that it's work is the force that's parallel times the distance. Okay, so it's force times the distance as long as the force is in the same direction as the distance. Okay, and by same direction, I mean same plane. Okay, you can have an object that is moving to the right, but your force of friction is going to the left. Okay, it's still going to do work because it's still parallel to the direction it's going. Okay. So yeah, that's pretty much it for this section. So let's do a couple examples. A few examples. So a 4.2 kilogram box is pulled 5.4 meters to the right along a frictionless level floor with a force of 14 newtons, 30 degrees above the horizontal. Now, you have to read these carefully because it says level floor and the force is angled. Okay, often kids will read this and say, oh, the block is on a ramp that's 30 degrees above the horizontal. Okay, that's not the case. It's a level floor. Okay, and the force itself is 30 degrees above the horizontal. Okay, so how much work is being done on the box? Well, the work being done on the box is going to be FAX times D. Okay, it's just this part of the force. And so we would say 14, and then that's adjacent to 30, so that'd be cosine 30 times 5.4, 4 meters. Okay, and that's it. That's what you're doing. So 14 cos 30 times 5.4 is 65.5 joules. Okay. Now, so that's part A, how much work is done on the box. So notice how I'm not doing 14 times 5.4. Okay, that would be incorrect. It's only the force that's actually causing the box to move. Now, how fast will the box be moving? So this is tying into the last thing that we just did where the net work is based off of the net force. And so if you think about it, the net force being done on this box is technically 14 newtons, 30 degrees above the horizontal, but we don't really care about that. We only care about the net force going in the X direction. Okay, so the F net X equals FA cos theta. Okay, so if that's the F net X, remember we have this W net So the net work equals F net times D equals delta EK. Okay, so now it's not a very specific question, but it should say it's starting at rest because it doesn't say that, but we can assume it's starting at rest. And so if we have our net work being our F net times D, and now notice how the F net here is only it still has to be parallel with D. Okay, just like up here, our force that's doing the work has to be parallel with D. So I can take those two. So F net X is FA cos theta times D, which is what we just did. So this is going to be 65.5. And that's going to equal to delta EK. Okay, and so that's going to be EKF minus EKI. EKI is assumed to be 0. And so all we have is 65.5 equals 1/2 mv squared. Okay, so it's this relationship between how fast something's moving, the gaining of kinetic energy, and the net work done on something, or the net force being done on something. So 65.5 times 2 divided by the mass, which is 4.2, and then square root that to get the velocity, we get 5.6 meters per second. Okay. Now, this is interesting because if we used kinematics, our VI would be 0, our A would be, do I need A? Okay, let me think about this. D is 5.4 meters. We want to know VF. Yeah, we need A. Okay, so A would be based off of the F net X, which is just FA cos theta, and then divide that by mass to get because F equals MA. So F divided by M is A. And so that's pretty much what we're doing. 65.5 divided by M. Okay. And then times 2 square root. Now, if you remember this equation, VF squared equals VI squared plus 2AD. Okay. Notice how there's a 2 here. That's the half because I multiplied by 2. And then the square root here where we're square rooting. So it's the same formula. We're just using energy to find it. Okay. That's where those kinematic equations come from. If you didn't understand it, that's fine. Okay, next example. So we have now friction on a box. Okay, so we have a box sliding along the ground at 4.4 meters per second, comes to a stop due to friction. How much work is being done on the box by friction? So the box is moving to the right. Okay, so it's going 4.4 meters per second. And then it's eventually going to stop. Okay, V equals 0, VF. VI equals that. Okay, and I know it's going to the right because this is positive. Okay, and that explains that it's going to the right. Now, the only force, this is a very hard concept to understand, the only force acting on this box is friction. Okay, and it's not in the direction of the box. The box is going to the right, friction's going to the left, it's stopping it. And so how much work is done on the box by friction? Well, the work is dependent on the change in energy. Okay, there's no distance here, so we don't know what the friction is doing and all that stuff. So we'll just use change in energy. Now, the energy that's changing is kinetic energy, so we're going to go EKF minus EKI. Now, EKF is 0 because it's stopped. Somebody muted me for some reason. Okay. Who keeps muting me? Okay, that's kind of weird. Oh, hang on. Can't hear me. Can you hear me now? Okay. Somebody was muting me for some reason. Okay, back to this problem. So the EKF is 0, so we're dealing with just the EKI. So this negative is that negative right there. And then EKI is 1/2 mv squared. So 1/2 times 5.6 times VI, 4.4 squared. Okay, so let's do that. 0.5 times 5.6 times 4.4 squared, which is negative 54.2 joules. Okay, so that's that part. And then, so that's the work being done by friction. Now notice how it's negative because friction takes energy away from things. It slows them down. How far does the box move before it stops? So now we can say, okay, so for part B, we're going to say how far does it go? So we're going to have to go work equals F times D. Okay, now this is technically FF times D, but because we have a change in kinetic energy, okay, that's what we're doing here, change in kinetic energy, then the work being done is actually the net work being done because it's only a change in kinetic energy. And so technically it's F net times D. We can use this work being done and it's the F net. Now in this case, if you look at our free body diagram, the F net is negative FF. Okay, that's the only force acting in that plane. So the F net is negative FF. So then we're going to go work equals negative FF times D. Okay, so if we do that, our work being done on the block by friction is 54.2 negative equals negative FF. Now, remember that FF is mu Fn. Now, in this case, your Fg and your Fn are the same thing. So this is going to be negative mu mg. And so we have 0.12 times 5.6 times 9.8. So 0.12 times 5.6 times 9.8 is 6.59 newtons. And I kept the negative there, but so technically it's negative because it's going to the left. So we're going to keep that there and go 6.59 here and then D. Okay, so you can use your dynamics skills to solve these problems. D equals 8.2 meters. Okay, any questions? Hopefully that makes sense. Okay, the important part is understanding that there's a relationship between W net and F net times D, and that directly causes a delta EK. Okay, this is a very, very important equation to know, or relationship to know. Okay, now this one's going to be a little bit harder. Do I want to give you guys time to do this first? Yeah, I'm going to give you guys a couple minutes to do this one, just to wrap your heads around it. Just try to set it up, try to get it. I'll just chill here, and if you have questions, you can ask. But yeah, I want you guys to try this one first, so go for it.
Excuse me, Mr. John. Mr. John,
Yep.
what does that mean? How much work is done for the question? Like, does it mean how many forces applying for the box or?
Well, okay, so let me draw the box and the forces that are acting on it. Oh, let me draw them a little bit lower. So there's the box being pulled to the right. Now it's being pulled by a force that looks like this. It's called
I
FA.
can see the screen. The
Sorry?
screen is gone. The screen is gone. I don't know why.
Oh. It's weird. Okay, there you go. Can you see that?
Yeah.
Okay, so you have the box, you have the FA going up and right, and then you're going to have friction going that way. So what you have is every force is going to do work. But when I say that, it's not really accurate. Every force that's in the plane of the motion of the box, every force that changes energy is going to do work. Okay, so that means that the FAX is going to accelerate the block. So it's going to give, like this one gives, or the box will gain energy. Okay, an applied force is an input of energy. It's giving something energy. The FF will take energy away. The box will lose energy. Okay, so when I say how much work is being done on the box, the FAX is giving the box energy, the FF is taking energy away from the box. How much total work is being done?
And there's no gravity. Gravity force does not apply to the box.
Well, so because that's why I'm doing it this way. The FF, so remember that FF is mu Fn. So technically, if we draw in the Fg and the Fn, Fn does not equal Fg because we have an Fay as well. So we need to figure that out eventually as well. Okay. Okay. Oh, one sec. Are we ready to go through it? I'm assuming some of you are probably stuck. Oh, is there no distance? Oh, there's no distance. We need a distance. Pull, let's just go 10 meters to the right. That would help. Let's see here. Can you hear me? I unmuted, so.
Yeah, we can hear you.
Yes.
Yeah, okay. Okay. Let's deal with the positive work first. So what work is the box, what energy is the box gaining from the FAX? So that's the easy one. So work equals FAX times D. And I'm going to do it a little bit differently after this, but let's just stick with this. So this is 13 newtons. So it's going to be 13 cos 30 times 10. So 13 cos 30, whoops, times 10. So that's going to be 113 joules, let's say. Okay. So that's the positive work being done. Okay, it's the FAX is in the same direction as the distance, so it's inputting energy. The work that the friction does is going to take energy away. Okay. Notice how it's negative FF because FF is going to the left. Now, in order to find FF, I need to deal with my F net Y. So F net Y is equal to Fn minus Fg plus Fay. Okay, so the net force in the Y direction is all the forces added together that are in the Y direction. So Fn is going up, Fay is going up, Fg is going down. Now F net Y is 0. Okay, it's not. Friction is on the right side. If friction were this way, that means the block is going that way. And so the displacement would be to the left and friction would be to the right. And so then work would be FF times negative D. And so your work would still come out as negative. Okay, friction always slows things down, so it's pulling energy away. Okay, and I know that the velocity would be to the left because the only way friction goes to the right is if something's moving to the left. Friction always opposes direction of motion. So Fn, that's what we're trying to find. Now, the reason why F net Y is 0 is because the block isn't moving up or down. Okay, the acceleration in the Y direction is 0. So when we go MA, AY is 0, minus mg plus FA sine theta. Okay, so to find Fn will be mg, so what's the mass? 5.6 times 9.8 minus 13 sine 30. Okay, so I'm moving the mg over and the FA sine theta over and solving for Fn. So Fn is 5.6 times 9.8, 54.88 minus whatever that is, 6.5. Right? Yeah. And so 54.88 minus 6.5 is 48.4. Okay, so that's our Fn. So now we can go work equals negative FF. FF is mu Fn, so we're going to go negative 0.14. Oops, 0.14. That's our mu times our Fn, 48.4, times D. Okay, so this is mu Fn times D. Okay, it's coming from right there. Okay, so FF is mu Fn, work is FF. Okay, let me rephrase this. Work is FF times D, negative FF. And then negative FF is mu Fn. So we're going to go negative mu Fn times D, negative 0.14. Did it again. Times 48.4 times our distance, which is 10. Okay, so times 0.14 times 10. And that is negative 67.7 joules. Okay, so in terms of how much work is being done on the box, we have positive 113 and negative 67. So the work, overall work being done on the box is 113 minus 67.7, which is 45.3 joules. Okay, now, because it's asking for how much work is done on the box, that's the net work being done on the box. Okay, the overall work is the net work. So we could have done it this way. W net equals F net times D. And then if that were the case, the F net would be FAX minus FF. And so we would just do the exact same thing. It would be 13 cos 30 minus mu Fn, so 0.14. Oh, I keep doing that. 14 times 48.4. And then we would take that times it by D and get the exact same answer as this, 45.3. Okay, so that's a pretty loaded question, but it's loaded because it requires you to do dynamics, which we haven't really done. But as I said when we first started this course, I'm assuming that you've done at least kinematics and dynamics, so that those are the assumptions I need to make in order to teach this course, because I can't go over those things. That's kind of a prerequisite for Physics 12. So if you haven't done those things, this is going to be a pretty hard unit for you. Okay, any questions? No? Do you guys want to keep going with conservation of energy? How much is there? Trying to determine whether I want to do this or not. What day is it? You know what, we have time. We're not in a rush. Let's not. I'm assuming you didn't get very far on the other worksheet, so let's stop for there for now, and then we'll do law of conservation of energy tomorrow. I'll probably have some sort of like assignment for energy. That was a sick question. Damn. Yes, it is. But that's Physics 12. That's a Physics 12 question. So, yeah, it's a lot, I know. I'll try to limit those, but that would be a hard question on the test. So there you go. You can accept something like that on the test. Expect something like that on the test. So yeah, we'll do conservation of energy tomorrow. I'll give you like a take-home assignment kind of thing, like what would normally be a quiz for the energy unit. And then we will start momentum on, what's tomorrow? We'll probably start momentum tomorrow. We'll do conservation of energy, and then we'll do the first lesson of momentum as well. Yeah, I think that's all. If you haven't handed in your test yet, please do so. The energy quiz would be tomorrow, so I would give it to you tomorrow, and then I would expect you to, I don't know, finish it by what's tomorrow, Thursday? Finish it by Friday? Yeah, probably by Friday. Okay, I'm getting lost here. Okay, where are we going? Okay, are there any questions about what I just did? Like, Any questions about this? No? Any other questions in general?
Mr. Stroop,
Yes.
could you just stick around for a minute? I want to ask you some questions from the worksheet. Earlier,
Yep.
my microphone was muted, so I couldn't ask anything.
Yep.
So, okay, thank you.
Do you want to ask them now? Like other people might have the same questions. So
Okay.
is it from? It's from the like worksheet we're doing now. The energy stuff.
No, it's actually the work 4.1.
Okay. Give me a sec. I just need to add that in. Worksheet package. Okay, go for it.
For number 3, I kind of don't know why the answer is 0.
Okay, so if you think about the pair being held 2.2 meters above the floor for 10 seconds, all it is it's being held there. So it's not, there's no change in energy. Because remember that work is a change in energy. So something has to change. Either the height has to change or the velocity has to change. But because the pair is just being held there, there's no change in energy.
Okay, then if it said someone was lifting it up, then there would be work.
Then
right?
there would be a change in energy. Yes.
Okay. Could you also go over number 7 and 9, please?
7 and 9. So 7 and 9. Okay. Pulled horizontally, frictionless, constant velocity. How much work is done on the passenger? Oh, so again, this one's going to be 0 because it's a constant velocity. Oh, wait, no. Hang on a sec. Yeah, this question doesn't even make sense. If something's being pulled horizontally along a level frictionless surface, it's going to accelerate. So that's impossible. But the energy is still going to be 0 in this case because it's a constant velocity. So if you look at your work equals delta E, the energy that would be changing is kinetic because it's not going up or down. But because it's a constant velocity, velocity is the same. So therefore your initial kinetic energy and your final kinetic energy are the exact same thing. So work is just 0. Does that make sense?
Yeah.
Hopefully.
Yeah.
This is why I said, like, you have 2 options, F times D or work equals a change in energy. Remember how I said this one would never lie to you? If you try to go F times D in this case, you could get an answer if you were trying to work out your distance and your force and all that stuff. But because it's not changing velocity, your delta E is 0, and therefore you get the right answer. Okay, and then number 9, pickle is accelerated from rest through a distance of the friction force between the pickle and what is the work done to move the object. So this one we're going to need acceleration. So we have rest, we have distance, we have time. So VI equals 0 starting at rest. The distance it travels is 6.0 meters in a time of 4 seconds. Okay, and so with that we can find our acceleration. Let me just read this for a sec. Okay, so with that we can find our acceleration, and then so that one's going to be d equals VIT plus 1/2 AT squared. It's been a while since I've done kinematics. I think that's what it is. And so it's going to be 6 equals VI is 0, so that's 0. 1/2 times A times 4 squared, so 16. So 6 equals 8A. A is divided by 2. So 3 over 4, 0.75 meters per second squared. And so that's your F net, or that's your acceleration. So your F net is going to be MA. So then you can go 25 times 0.75. Okay, so to find your F net, so 25 times 0.75, which is 18.75 newtons. Okay. Now it's asking for the work done. So the work done, that like there's going to be an FA that's actually accelerating the pickle, and then FF is slowing it down a little bit. But because you have the actual acceleration and you can plug that into your FNet formula, you can get the net force that already counters in the friction force. So all we need to do is take that 18.75 and multiply it by our distance, which is 6, and we get our, nope, that doesn't work at all. What is the work done to move the object? Okay. Work done to move the object. I read this wrong. See, this is very, very tricky. So the work done to move the object is done by the FA. I read it as what is the work done on the object? It's what is the work done to move the object? Okay, so the language gets very, very specific in this case, which I just screwed up. So very, very easy to do. So based off of our FNet, we have an FA going to the right and an FF slowing it down. Okay, I just found out that I found my FNet, but FNet is FA minus FF. And so the net force is 18.75. I don't know my FA, but I know that FF is 3.8. And so 18.75 plus 3.8, my FA is 22.55 newtons. Okay, and so then when I'm trying to find the work that's done to move the object, which is done by FA, my formula becomes that, work equals FA times D. So 22.55 times 6, 135 or 140 joules. So that's what the answer is. Again, it's kind of good that I screwed up the language because it shows you how easy it is. You really have to read these very carefully. And on the quiz or the test or anything like that, you can say, hey, like, just ask for clarification if you're not quite sure. Okay, and then I'll tell you what. I'm going to try to make it as specific as possible so that we don't run into these issues, but sometimes the language is inevitable. So, yeah. Any other questions?
Can you go over number 6 together?
Number 6?
Yeah.
Yeah, so the student runs at a constant velocity up a flight of stairs. So constant velocity means that delta EK is 0. It's not changing. If the height of the stairs is 3.2 meters, what is the work done against gravity? So in this case, the work done is a change in EP, delta EP. The student starts at the bottom of the stairs, so the EPI is 0. The EPF is not 0, it's going to be MGH. So all I need to do is work equals MGH. So that's going to be 60 times 9.8 times 3.2, which is, what's the answer? 1900. Okay, does that make sense? Even if it didn't say constant velocity, it's still like you can assume that they're running up the stairs, but they start at 0 and they end at 0. So there's no real change in kinetic energy, like from start to finish. Anytime it says height or like, yeah, the word height, it means potential energy.
Okay. Thanks.
Yeah. Anything else?
I just want to clarify something.
Yeah.
Okay. So if the velocity is constant, the net force is always 0, right?
Correct.
And if there's acceleration, the net force is either positive or negative.
Right. If the acceleration is in the positive direction, so it's speeding up, then the FNet, well, okay, so let me be specific here. If the velocity is that way and the acceleration is that way, F net is positive. If the velocity is that way and acceleration is that way, then F net will be negative. If the velocity is that way and the acceleration is that way, then F net will be positive. And if the velocity is that way and the acceleration is that way, F net is negative. Okay, so notice how it depends on the acceleration every time. Acceleration is to the right, therefore it's positive. Acceleration is to the left, therefore it's negative. Acceleration to the right, positive. Acceleration to the left, negative. Okay, but the difference between these things is this is speeding up. This is slowing. This is slowing down. And this is speeding up. Okay, so if acceleration is in the same direction as velocity, it's going to speed up. It's going to get faster. But if they're opposite, it's going to slow down.
Could you also draw what happens when the velocity is constant?
So
Like
if velocity is constant, like this,
why it's 0?
then A is 0, which makes F net 0. It doesn't mean work isn't being done. It just means the net work being done is 0 because the energy isn't changing.
Okay, so it's still moving, right? Even if
it's still moving, it still has energy, but the work being done is 0 because the work is a change in energy.
Okay, yeah, now I got it.
Yeah. If you're ever stuck, like and this goes for everyone, if you're ever stuck, there's 2 types of energy here. There's EK. I don't know, I'm doing delta. There's EK and there's EP. Okay, this is dependent on V. This is dependent on height. If the V is changing, there's work being done. If the H is changing, there's work being done. If the H doesn't change, the EP isn't changing. If the V doesn't change, the EK isn't changing. Okay, so it all comes down to, you can just ask yourself, is it moving? Yes or no? Is it changing motion? Yes or no? Is it getting higher? Yes or no? Okay, so and that's what I would do, like in this case for number 3. Okay, oh, is it changing height? No, it's not, therefore work is 0. For number 7, is it changing velocity? No, it's not, therefore work is 0. Okay, so you always have to think about the state of energy that it has and compare the states. If the states of energy are changing, there's work being done. If they're not, then there's no work being done.
But for 3, it's changing the velocity, right? Because the force is applied.
For number 3?
Yeah.
No. No, because there's nothing about change. It's just being held there. It's being held above the floor.
Oh, okay.
It's being held above the floor via 0.
Mm-hmm.
Okay, and if V is 0, then there is no kinetic energy, and there's no changes in kinetic energy because it's just being held there. And the potential energy it has potential energy, but it's not changing potential energy.
All right.
Okay, so therefore the change in energy is 0. So the work is 0.
All right, thank you.
Yeah. Okay. I'm glad we didn't do conservation of energy because it's good to go over questions like this. So you guys can finish the EP and EK worksheet, and then we'll do conservation of energy tomorrow, and then we'll start talking about, we're not going to do power and efficiency because that's technically physics 11 stuff. So we'll get into law of conservation momentum. Well, not law of conservation. We'll get into momentum tomorrow as well. Okay. Okay, so that's it. That's all I got for today. So I will see you guys tomorrow.